Good afternoon, and welcome to the Center Stage Seminar Series event. My name is Tiffany Willoughby, Education Programs and Outreach Manager in the Office of Research at the University of Texas at Dallas. I will be your host. Joining me today is Dr. Mario Rotea. Mario A. Rotea is the holder of the Erik Jonsson Chair in Engineering and Computer Science at the University of Texas at Dallas, where he is also the department head of mechanical engineering and the director of the Center for Wind Energy. Rotea spent 17 years at Purdue University as a professor of aeronautics and astronautics, developing and teaching methods for the analysis and design of control systems. He also worked for the United Technologies Research Center as senior research engineer on advanced control systems for helicopters, gas turbines, and machine tools. Rotea was the head of the Mechanical and Industrial Engineering Department at the University of Massachusetts Amherst, where he expanded the department in the area of wind energy and applications of industrial engineering to the healthcare sector. His career includes terms as Director of the Control Systems Program and Division Director of Engineering Education and Centers at the National Science Foundation. Rotea is co-founder of WindSTAR, an NSF Industry University Cooperative Research Center aimed at bringing together academia and industry to advance wind energy through industry-relevant research and education. Rotea joined UT Dallas in 2009 to serve as professor and inaugural head of the then newly created Mechanical Engineering Department. He is a fellow of the IEEE for contributions to robust and optimal control of multivariable systems. Rotea graduated with a degree in electronic engineering from the University of Rosario. He received a master's degree in electrical engineering and his Ph.D. in control science and dynamical systems from the University of Minnesota. Please join me in welcoming Dr. Rotea as he takes center stage in the spotlight. Dr. Rotea, welcome.
So good afternoon, everyone, and thank you, Tiffany, for your introduction. I wanted to, before I get started, acknowledge the contributions and support of the University of Texas at Dallas that has given us all the resources that we need to get to where we are today in terms of wind energy. In particular, I want to thank Dr. Pancracio for his support through the center initiative that has allowed us to formally create an organization by the name of UTD Center for Wind Energy. So what I'm going to do today is talk about what is the Center for Wind Energy, who is there, what do we do, what are our goals, and then talk a little bit about the research that has been done over the past several years at UTD in wind energy in my own area, which is control systems. So let me get started and look at this slide where I wanted to give some context to the audience for the motivation for doing work in wind energy at UT Dallas. So this is to the left, what you see is a map of the wind speeds in the United States. And the dark purple is high wind speed and the green is low wind speed. And what you can see in there, these are wind speed at approximately 80 meters height, which is the height of the average height for the hub of the rotor for a typical wind turbine. So what you see is that the wind is high in the middle of the country. That's the Midwest, and Texas. All the middle of the country has quite a bit of good wind. As a result, this has been exploited, and today wind power is the #1 source of renewable energy producing electricity in the U.S. It has about 100 gigawatts of installed capacity, and to give you some calibration, that can power 30 million homes. That's quite a bit of installed capacity, and we want to get some more. There are approximately 59,000 wind turbines in operation, And then with all this installed capacity for wind power and number of wind turbines, the country on average is producing about 7.2% of its electricity from wind, which is not a high number, and the objective is to get that to be to higher levels. On the right-hand side, you see a map color-coded by the amount of electricity that is produced in each state. As I said before, the total US average is about 7%, and then the states that are in the middle of the country are the ones that are producing the most electricity from wind. And it is us, Texas, with 18.5%. There are other states that produce more, but they have their population is smaller, so one has to take that into consideration. They have actually less capacity, less installed capacity than Texas. So let's look at Texas in particular now. And this is wind energy in Texas. So the state has about a third of the installed capacity in the country is in the state of Texas. What you see in this map are in black, where the wind turbines are located approximately, and these gears in gray are manufacturing facilities and other facilities to assist and develop the operation of wind projects. The state has about 15,000 wind turbines. Again, that's a good number relative to the 60,000 that are in the country. And what is interesting is that we produce much more than the average. The average in the country is 7% electricity from wind, but this state is producing 17.5. Something that is not well known, but is very important to mention, is that wind energy is good business for Texas. And the state in particular receives almost $300 million in state and local taxes, which is a great source of revenue. And owners of land are receiving approximately $200 million in annual land lease payments from the wind projects. So bottom line is Texas is really king in wind, and if Texas were a country, it would be number 5 in the world in terms of installed capacity. So what are we doing at UTD, given the fact that we are in a state where wind is so important? Well, we have a group. We call ourselves the Center for Wind Energy at UTD, or UTD Wind, as one of my colleagues once suggested. And the goal of the work we do is very simple. The name of the game in research development to support the growth of the wind industry is costs. The United States wants to get to 400 gigawatts, so 4 times what we have today, by 2030, with penetration levels of 30% or even more in the electric grid. So to do that, we need to continue working in order to lower the cost of wind energy. And we do 2 things. We do research that is transformational, where we're trying to discover new concepts for the production of wind, the transmission of wind, the interaction of wind with the environment, and research that is more translational or applied research, where we take ideas that have been tried elsewhere or are known to be good, and we apply them to wind because they have not been applied before. In terms of our mission, we want to put people together. This is the more the merrier. So we want to connect researchers in industry, in universities, with students in order to enable our activity. An important part, we are a university, so students are central to our mission, and we want to train the next generation of wind energy innovators. And everything requires collaboration. And collaboration also requires funding. So we want to establish private-public partnerships in order to enable our work. The picture that you see at the bottom was the last on-site meeting of one of the activities we do within the Center for Wind Energy, which I will describe in a minute. And that was done last January here at Dallas, at UTD. So I thought that it was a good idea to give you a sense that happened to get to where we are. And the first thing that actually happened, and I'm presenting these milestones as essentially what awards have enabled and what investments have enabled the activity that we do. I use that in order to describe the milestones. So the first thing was getting together with the University of Massachusetts Lowell in order to develop a proposal for the center to the National Science Foundation. This center is called WindSTAR. It was funded in 2014 by NSF, and I will talk about it in the next slide, so I don't want to spend too much time here. But the important thing is that this is a collaboration between UMass Lowell and UT Dallas, where we complement each other in order to address the needs of the wind power industry. 2014, another great year for us. Former President David Daniel made a commitment, and Mark Spong made a commitment to build a wind tunnel for doing experiments, and that's a very important facility. So UTD made a significant investment to provide us with a wind tunnel that can be used for wind energy, but it can be used for other things as well. And I will just refer to the wind tunnel today as it's using in wind energy. 2018, wind tunnel is completed. We call it BLAST, boundary layer and atmospheric boundary layer and subsonic tunnel. And it opened in 2018. You see a bottom here, a picture here at the bottom with the day we actually did the opening ceremony for the wind tunnel. And 2018 was another great year for us, because one of the company members of our WindSTAR Center wrote a proposal based on some of the data we did in a project with them, and they were awarded a significant grant, significant contract from ARPA-E, which is an organization of the Department of Energy. This company is by the name of Aquanis, and they gave us about $1 million to collaborate with their team in the development of active load control systems for wind turbines. Then we go 2019. 2019, again, two things happen. One is internal, the other one is external. The external one is this center, WindSTAR. These go by phases. Phase 1 is 5 years, phase 2 is for another 5 years. We were renewed for the second set of 5 years with an award for a little over $1 million for the two campuses, UMass Lowell and UT Dallas. And internally, the Office of Research, under the leadership of Dr. Pancracio, selected us through a competitive process for seed funding to create the UTD Center for Wind Energy. So things keep going well. And in 2018, 2020, this year, we are awarded a large grant to develop new concepts for offshore wind power. And I have a slide about these two, so I don't want to spend a lot of time here. But this is the sequence of events that took us to where we are today. So WindSTAR, what's WindSTAR? So WindSTAR is NSF Center for Wind Energy Science, Technology, and Research. That's the acronym for it, is WindSTAR. It has a website. The website is down here. And this is the collaboration that I mentioned between UT Dallas and UMass Lowell. And I'm going to turn my cursor into a pointer so that I can, so a collaboration between UT Dallas and UMass Lowell. The mission is conduct research of significance and relevance to the wind power industry and produce their workforce at all levels. Leaders that could come with new innovations and contributors that can take some of the research that we do in WindSTAR to their companies. The entire concept of these centers is NSF give us money for operations. That's why the grants from NSF are not huge. And then we are supposed to raise the funding for conducting projects from the member companies. So this time we have 15 member companies. They are all listed here. And, this number could be larger. And we work hard with our colleagues in Massachusetts to continue to get more members. But what's very important is that we, since the very beginning, we had a very good coverage of the wind power industry. And by that I mean we have the entire supply chain from the original equipment manufacturer like GE, they make wind turbines, to the that own and operate the wind turbines to sell electricity to the grid. And these are EDP Renewables, Leeward Pattern, and Shell. And then in between, we have component manufacturers like TPI that makes blades, or Bachmann that makes electronic controllers, Hexion, that Huntsman, they make some of the chemistry. So in the middle, there are component suppliers and service providers to both ends, the owners and operators and the original equipment manufacturers, the OEMs. The center has been doing quite well, and we have completed in the first phase more than 30 projects, develop a number of computer codes for analysis and design, a few hardware prototypes, and produce Ph.D. dissertation, master students, journal publications, all the traditional metrics of an academic organization, but with an emphasis on giving industry what they need as well. And on top of that, we have created with WindSTAR as the mechanism for networking, we have created teams in order to respond to larger funding opportunities from the Department of Energy. The total investment from industry in the last 5 years have been a little over $1.5, $1.7 million, with an even distribution in terms of projects between Massachusetts and Dallas. It's not advancing. Okay, so what type of research is done to support the wind power industry in our center? I assume that some of you had an opportunity to look at a video that was sent by Tiffany in the Office of Research from the Department of Energy, explaining how wind turbines work, what happens in land, and what's the future for offshore systems. But if not, let me just say that a wind turbine by itself, it looks like a column with three blades, but it's a very complicated system. And that's the turbine alone. It even is more complex when they operate collectively in what we call wind farms, because one turbine alone is not enough to justify the capital investment. You need many, and that's what gives rise to the concept of a wind farm. So if you look at a single turbine, you see that there are blades, and there is what we call the rotor system, and that's some of the research that by our faculty is done in that area. The research in wind needs to be, every other area needs to be supported of technology, needs to be supported by modeling using physics and understanding of the processes that go all the way from atmospheric processes and the wind to the production of electricity in the grid, as well as making measurements. So we have faculty that do modeling for power production, modeling for the aeromechanical loads that these machines need to sustain. We have wind tunnel testing, and a faculty member doing measurements, field measurements of the wind using an instrument called LiDAR. I'll address that in another slide. Another area, these machines need a control system. Everything is moves towards automation, towards automatic operation of all these assets. And for that, you need to connect sensors with actuators through some algorithm that tells the actuators what to do given the measurements. And that's what we call a control system. So we use control systems to optimize the energy capture. We use control systems to reduce the impact of the mechanical loads on the machine so that they can last longer and have no problems. And we do this both at the turbine level and at the wind farm, wind plant control level. Now you get your power from the wind, and that moves a shaft that we call the high speed shaft, and that low speed shaft is connected through a gearbox to a generator. And that generator then connects through a power electronics that provides energy to the grid. And so we have green integration activities as well as ambitions to develop more activities in energy storage. In addition to these four thrusts that I described, we have some faculty looking at different materials, different structures for foundation and towers. This is a very expensive part of the turbine. These things are very tall. When I started, I said wind measured at 80 meters height, and that's because that's the average height for a wind turbine in the country today, but things are going to get a lot taller. So this is a very expensive and important part of the structure that requires research in order to lower the costs. And then the whole area of inspection and repair, this is something that we're trying to develop. You know, drones are everywhere. We want to use drones and robotic technologies in order to assist humans to do their job in remote areas where the wind farms are located, or even to develop ways of repairing machines without having to bring down a generator or a gearbox to the ground in order to solve that problem. So the three arrows that you see here, arrows where these are research areas that are directly connected to WindSTAR. And if you go to this website, you can download this report and you will see public information on the projects that we have completed in WindSTAR from both campuses. So WindSTAR is not the only thing. It's probably, I would call it the seed for everything, the foundation for the Center for Wind Energy at UTD. But there are two other major things that are that fuel our activity, and these are two major grants from ARPA-E, the Advanced Research Project Energy Agency for Energy, and that's is in load control for wind turbines. And the objective of this project is to develop control systems that allow the blades to last longer by carrying less loads. And this is led by one of the companies that is in WindSTAR, Quanis, and the UT Dallas PI for this effort is Dr. Griffith, and myself and Dr. Jungo are his co-PIs. So Dr. Griffith has responsibility for the entire project at UTD, the rotor design, the blade design. I do the controls, and Dr. Jungo does the wind tunnel testing for the actuators that we are going to use to enable this project. This project has its lead organization, this company, and then team members us, a blade manufacturer, TPI, who is also in WindSTAR, and a national lab. And this is the typical winning formula for large grants. Small business, large business, a university, and a national laboratory, they can pull together the resources they need to deliver. On the right-hand side, this is one that thanks to the leadership of Dr. Griffith, we won in a new program created by ARPA-E by the name of Atlantis. Atlantis is looking for brand new concepts in offshore wind energy. And UT Dallas has proposed a new vertical axis wind system at the level of 15 megawatt or even higher. And the partners here are, again, some of the players that we have here, but also new players that work on the offshore domain in terms of vertical axis machines, as well as platforms. And then another partner university that has expertise that we currently do not possess in the area of design optimization. So these are important investments, and they keep us busy. Obviously, research, we are a university, and there is an intimate connection between research and education at all levels. So here are 4 pictures that describe how that interaction happens and what are the things that excite the students. So on the left-hand side, at the top, you see a group of students with a mobile station going to make wind measurements at one of the Texas wind farms, On the right-hand side at the top, you see an undergraduate student and a former graduate student who is now in the center as a postdoc discussing computational results. On the bottom left, there is a student from the Technical University of Munich who came to our wind tunnel. This is his small wind turbine, the G06, and he came here to do some testing. And on the right-hand side, you see interactions between graduate students and members of industry in our industry advisory board for WindSTAR talking to one another. Now, who makes all of this happen? These people. So these are the faculty that are in our center. The ones in red are foundational pillars. Wind energy at UTD, covering control system, the rotor and the turbine as a system, all the measurements that are required for the flows that create power, and all the modeling that is required to understand how to produce power, what are the loads in a machine. And others are essential faculty members in our center who on and off interact with us and do projects, and we want them interacting more on than off. The bottom line is that we have about 62, there are 16 people here, and 10 of them have active projects in wind energy, and that is excellent. That I think makes a center. A center is one person show, is a collective group working together. So facilities, what do we have? I mentioned the wind tunnel. Is again, I acknowledge the vision and support of David Daniel and Mark Spong to get this off the ground. And it's phenomenal. I mean, there's only one of a kind wind tunnel like this with a very long test section to create at the scale real conditions for the flow that wind farms see. And on the right, you see the two turbines from Technical University of Munich with the first paper, I believe, that we did with them in making measures their wakes and their power production in blast. If you want to know more about this wind tunnel, you should contact Dr. Jungo. This is the LiDAR facility. It's a truck with the trailer that has all instrumentation. We have two LiDARs. These are a laser. A LiDAR is like a radar, but instead of using electromagnetic signal, you're using light, a laser, to get a return and try to estimate the wind velocity of the particles in the air. So we have two of those, and one of them is shown here on the cover of the most prestigious publication in wind energy today. It's called Wind Energy of Wiley, and this is the cover of November 17 for wind energy, where Professor Jungo and his students publish an important paper on how to use a LiDAR to extract information that is necessary to predict the wind, and from there to the diagnostics on the ability of a wind farm to produce power. Okay, so I give you an overview of the center, facilities, people, motivation for what we do, and some of you I know that are students in this audience. So how about the research? Well, I'm going to pick a topic that I know, which is control of wind turbines, and describe some of the work that we have done in this area. And this topic is extremum seeking control. So extremum seeking control is essentially an algorithm that is used to maximize power production in a particular region of operation of a wind turbine. It's called region 2. And region 2 is the wind speed where the generator is running at an RPM and rotor speed that is not exceeding its rated value. How do we use this algorithm? Well, it can be used in two modes. It can be used for a single wind turbine. It can be used for a wind farm if we allow coordination of the different controllers for the different turbines. And what it does is continuously retune the machine so that it operates at its peak performance. Continuously retune a wind farm so that they don't fight each other for the wind, but they cooperate and collaborate in order to maximize the power they can extract together. And here in the middle, you see some of the reasons of why this may be needed. This is a simple algorithm. It's based on, if you know any optimization, this is based on the steepest ascent, the gradient algorithm, to find an optimal set of parameters. If you don't know optimization, but you have done hiking, if you want to get to the top of the hill, you have to climb up. When you're at the top, if you want to go down, you have to climb down. So there is a slope up, slope down. When you're at the top, the slope is zero. So that's what the Extremum seeking does. It takes you to whatever peak value your power has for the particular conditions. The work that I will describe is collaborative work with Professor Leonardi and Professor Lee from mechanical engineering and from the center, as well as former graduate students that completed their PhD by working in wind energy. So before I start with any controls, let's talk about how turbines operate. Basically, a wind turbine produces power when the wind is sufficiently high, and we call that the cut-in speed, to move this massive rotor. And here you see a GE 3.6 megawatt machine in comparison to a Boeing 747. So you need enough energy in the wind to start the rotor. And then if the wind is too high and you apply it to the rotor, you will lose it. So you shut down the machine. So you produce power between the cut-in and the cut-out wind speed. And the way power is produced in this region depends on how much wind you have. There is a critical speed that we call the V-rated, the rated wind speed. And at that speed and beyond, the power output is constant. And this is the rated power of the generator. You know, you buy a generator that is a 3.6 megawatt generator, the rated power is 3.6 megawatt. You buy one that is 2 megawatt, the rated power is 2 megawatts. But below rated is where you depend a lot on the aerodynamics of the machine and where you want to maximize efficiency. So what is the power extracted by this machine when the speed of the wind is below rated conditions? Well, that power is essentially proportional to the power available in the wind. The power of proportionality is the efficiency, the aerodynamic efficiency of the machine. There's also an efficiency for the generator, but I'm going to just focus on the aerodynamic efficiency of the rotor. And we call that CP. And the power available in the wind is proportional to the swept area of the rotor, which is proportional to the square of the radius of the blade, and this is why longer blades are better. And it's also proportional to the cube of the wind speed in this region. So this is a cubic function of wind speed. And the objective of region 2 control, we don't control the wind, we don't control what's available in the wind, but we can control the efficiency. So the objective of region 2 control is to maximize the efficiency. So how is that done in a real machine? Well, in region 2, machine is controlled by controlling the speed of the rotor. And the speed here in the wind power community, we use this nomenclature that we call the tip speed ratio. Essentially, the tip speed ratio is the linear velocity of the tip of a blade, the angular velocity of the rotor times the length of the blade, the radius of the rotor, divided the incoming wind speed V perpendicular to the rotor. We call that number lambda, and that's the tip speed ratio. And now if you were to plot for a typical turbine the efficiency, the aerodynamic efficiency or the power coefficient of the machine as a function of the tip speed ratio, you get this. So if the T-speed ratio is very low, there is no power. If the T-speed ratio is very high, there is no power, there is a sweet spot. If you operate at that T-speed ratio, you're going to maximize your efficiency and you're going to get the most power for the given wind. So the name of the game with speed control is keep me operating at this star. Keep me operating at the optimal T-speed ratio. In this case, this is a 5 megawatt turbine model from the National Renewable Energy Laboratory, and it has a 0.5 CP max at about 7.5 T-speed ratio. These machines, I don't think there is one that has efficiency bigger than 50%. And there is actually a limit called the Betz limit that no one can exceed. But I'm going to skip the theoretical part. So how do we control the machine to operate at the optimal tip-speed ratio? The optimal tip-speed ratio is right here in this star. And on the left, you see the TSR, and we said that 7.5 was the optimum, and on the right is the power coefficient. So I'm showing here the TSR and the power coefficient in yellow. You see that we hit the star at about 20 minutes using this basic algorithm called Extremum seeking. But in this animation, which has the turbine and the time trace at the top, this is the turbine. When the colors are green, is because or darker, is because the wind speed is low. When it's red, the wind speed is high. So we start accelerating the machine, and the wind speed behind it keeps decreasing, but the machine starts more power. So using Extremum seeking under very ideal assumptions is quite easy. I mean, we could if we can adjust the rotor speed instantaneously and measure the power and have no turbulence, no noise in our measurement, no changes in wind direction, then this problem is easy to solve. But the reality is different. And the reality, first of all, does not allow us to control speed automatically. In your cars, you cannot change from 20 miles per hour to 60 miles per hour in no time. You need a force, a powertrain, a force actuator in order to achieve that. And here, what is used is the generator torque. The generator that is capturing power from the rotor and putting it into the grid, and that requires a torque. And the reaction torque of the generator is applied to the rotor, and it acts sorts of a brake. You can imagine a bicycle. You are at the top of the hill, and the brakes in the bicycle, you start speeding up, you want to reduce your speed, you start touching the brakes. That's a reaction force that is slowing you down. So you can think of the generator torques as braking a bicycle. Well, it turns out that in order to operate at this point, at this optimal CP and given optimal TSR, you have to choose the generator torque as an appropriate function of the generator speed, rotational speed omega g. And that function is essentially a constant times the square of the generator speed. It could get more complicated than this, but this is the beginning. So if you know the aerodynamics of the machine and you know exactly what your optimal CP is, or maximum CP, at what lambda value it starts, you know the density of the air, and then you know the geometry of the machine, which is lumped into this thing called constant, then you can calculate the best value of this parameter to put here and achieve optimality. Stay at this point no matter what happens with the wind conditions. We don't know these things. And even when we do, they could change. So let's take a look at what could happen for a real wind turbine. So you buy a wind turbine today, you'll put it on the field. They are supposed to last 20 years. You go 2 years after you install it, maybe a year after you install it in Texas, and you start seeing that the blade has these insects. These bugs change the aerodynamic efficiency of the blade. You put wind turbines in Canada or in the northern plains in Minnesota, and you start seeing this. That's ice on the blades. That changes the aerodynamics. And then if things are really bad, you could get erosion of the leading edge, and you basically have a blade that needs to be repaired. But what does all these things do to your ability to extract power, essentially to the aerodynamic efficiency called power coefficient? So this is the operating point. You can think of this as the tip-speed ratio. It could be some other parameter, but let's assume it's a tip-speed ratio. You buy a new machine and you operate on the blue curve. The manufacturer not only gives you a high value for your CP max, but also a flat curve, so that if your operating point changes a little to the left or a little to the right, you are still near optimal aerodynamic efficiency. The problem is that this is for a new machine. When these effects take on, this curve could become the curve in red. And if that were to happen, your optimum goes down, but not only the optimum goes down, the curve may get a lot sharper. So if you continue to operate here because you didn't know that these changes took place, then you can, instead of producing this, would be producing this amount of power. And what the extremum seeking control does is to take you from here to the new operating point. You will still lose, but this is a change of software that restores some of the lost power without having to change any of the hardware in the blade. Is this significant? It could be. It could be 1, it could be 2%, and that has money implications for this industry. And in some cases, adjusting just the TSR is not enough. You may need to adjust also the so-called pitch angle, which is the angle the blade makes relative to the wind that is impinging on that aerodynamic surface. So bottom line is, if things change and you don't change your software, you're going to lose power and you're going to lose money. Our value proposition is, what changes can we do with software because before things get so bad that you really need to do a hardware repair. And our answer to that is what we call extremum seeking control, where we make measurements of the rotor power, then go through an algorithm that I'm not going to get into the details. And that algorithm can adjust 2 of the main parameters that control the aerodynamic efficiency of the blade. The torque gain KT that I mentioned earlier, and the blade pitch angle. Okay. The algorithm has some good properties, doesn't require a lot of information in order to set it up. In terms of measurement, we don't need to measure the wind. That's a big thing because measuring the wind is not easy unless you're willing to pay a lot of money and get a LiDAR on the machine. And this algorithm can be used to control the torque gain, the pitch angle, or both together. I need to start accelerating here. So we did an implementation of this in an experimental machine that is owned by DOE in the National Renewable Energy Laboratory. It's called CAR3, and it's shown here. This is a 700, 600 kilowatt machine, fully instrumented in order to do control studies. And when we did the test, we applied our algorithm to a baseline controller that was set. This machine has an optimal CP, which is calculated under a number of assumptions that is 0.47. We started with a controller that the machine had, producing an approximation of the power coefficient, which is essentially the power of the produced by the turbine divided the power available in the wind, that it was 0.38. Then we let that machine run, we applied our ESC, and we increased the power coefficient to 0.4, or the estimated power coefficient to 0.42. So that's a 12% improvement. We did the same for the pitch angle, which is the angle that these blades make relative to the wind. And we took it from a baseline of 0.32 to 0.35, which is an 8% improvement. And the difference in improvement had to do with several factors, and one of them is that the torque gain experiment was done in the summer. No ice, nothing funny on the blades, maybe some bugs, but not that many. And in the winter, some ice on the blades, they change aerodynamic properties. So we published this work. So in terms of improvement and impact, we have learned that ESC can improve power production. This experiment had a limited amount of data, and with the data that we had, we were able to do some statistics, and we can say with 90% confidence that our improvement is going to be at least 3 to 4%. I mean, we may not get 8, we may not get 12, but we should have some confidence that we can get at least 3. And of course, more testing is needed, but these results were encouraging. And why is this important? Well, we talked to the people in industry. These numbers are a little dated now. They could have changed. But once we were told by members of the Industrial Advisory Board of our center that a 1% increase in annual energy production for a wind could translate in an increase of revenue between $3,000 and $5,000 per year per machine. So if you take these numbers, you assume a 2% increase in AAP by applying this ESC, and you do this as a retrofit to roughly 20% of the 60,000 turbines in the country, you're going to have an extra revenue between $1 million and $120 million. So that is very promising, very encouraging, and we should do this algorithm more and more. But unless we get into some details of how extreme seeking control work, we may not be able to realize this benefit. There are some unresolved issues. So we continue the work, and I will try to be very quick on this. I said earlier that extreme seeking control aims at taking you to the peak, the hill, the top of the power curve, of the power coefficient curve. So essentially, you know that you are at the top when the slope is 0. You neither tilt to the right, not to the left. You don't tilt. So the extreme seeking control is essentially using a measurement of power to take it to the point where the slope of the power relative to the control parameter, that's your hill climbing mechanism, and it could be the tip speed, the torque gain, or the blade pitch. So the derivative, which is the slope relative to that control parameter, needs to go to 0. If you hit 0 with that, then you know that you are at the peak, because this function is a unimodal function of the parameter that we are using to control it, be it the torque gain or the blade pitch. But when you do an analysis and you look at the power that comes out of the turbine as a function of the control parameter, let's say the torque gain, and the wind speed, I said that the power is proportional to the power available in the wind times the efficiency. The power available in the wind depends on the cube of the wind velocity. And the wind velocity in region 2 can go from 3 meters per second to 9 meters per second. That's a factor of 3. So 3x. Then 3x to the cube is 9. So you can see a factor of 10 change in the properties of this feedback loop. And when you do that, it's something not very welcome by a control engineer, because you're changing what we call the loop gain of this control system by a huge number, a factor of 10. So what happens is the basic extreme seeking, unless you do some fix, becomes very sluggish at low wind speed. Gain of this loop is small, and it could be very aggressive, even unstable, when the wind gets very high. So it's difficult to commission. You have to babysit the algorithm each time you detect a change in wind speed, and that's not very practical. So a few years ago, I asked the question, is there a measurement or a transformation of the power signal that I can find that if I maximize that new function, I'm also maximizing power, but the derivative of that function with respect to the control parameter is independent of Pwin. And the answer is yes, that transformation exists and it's the logarithm. If you take the logarithm of this product, then you have the logarithm of the sum. If you calculate the derivative of this logarithm with respect to the control parameter, this term completely drops, and you are essentially proportional to the power coefficient. So if you could actually take the derivative of the logarithm with respect to the control parameter, you are essentially maximizing the power coefficient. This was a very nice theoretical observation, which is also very simple. So then we apply this gradient to the gradient algorithm that says, hey, adjust the derivative of the control parameter with respect to time proportional to the gradient that you measure, so that when you are in steady state, this gradient is 0 and this quantity is 0, and as a result, you are at the peak of the power curve. And the transient response of this loop does not have the wind speed in it, and as a result, is completely insensitive to that. So then got together with Professor Leonardi and a former student, Umberto Ziri, and we did some simulations that they know how to do using the high fidelity large eddy simulation capabilities. And we look at how well was this idea performing relative to the baseline or the naive ESC, I would call. So what we did is take a model wind turbine, calibrate it at 8 meters per second wind speed, and then evaluate it at two other wind speeds, 4 and 12. Now I need to move really fast. So this is the calibration stage. On the left, vanilla ESC, on the right is the log power ESC. So at the top, you see the generator torque gain. This is the control parameter, and at the bottom, you see the power coefficient. Forget about the tip speed ratio. So these blue lines are the optimal values for all three. And if we start ESC from the wrong value for the torque gain, then ESC converges to its optimal. And we calibrated the ESC, the vanilla ESC, so that converges to the optimal happens in 10 minutes. We did the same thing for the LP-ESC, and they both behave equal. Okay, in 10 minutes, even if they start from the wrong control parameter, they converge to the right one, and they hit the maximum aerodynamic efficiency. But what happens? Applied two other wind speeds in region 2, a lower one of 4 meters per second and a higher one of 12, we see what I told you. At 4 meters per second, the vanilla ESC takes very long to converge. In fact, it takes quite a bit. We started with 10 minutes and now we are at 50. Okay, so 5 times longer. And if the speed is very high, the algorithm becomes unstable. Here we're hitting 0 power, even negative power. So you cannot use this in a real machine. On the other hand, if you go to the log power ESC, the 3-time series for the 3 wind velocities are sitting one on top of each other. This shows consistency across different wind speeds, repeatability of the algorithm as calibrated, and is a very encouraging result to go to the field with something like this. So what have we learned after doing this research? And what have we learned in today's presentation? Wind turbines have a sweet spot when they operate at peak efficiency. That sweet spot could change due to a number of factors over the lifetime of the turbine. LP-ESC is an algorithm that allows you to retune to the new sweet spot every now and then, We actually have a patent on this issue and are in conversation with the company to license this technology. And the algorithm itself could be a good retrofit for aging turbines or turbines that are put in off-design conditions, such as complex terrain that was not taken into account when the machine was designed. On Friday, I give another webinar, now sponsored by the University of Massachusetts Lowell, where I will expand. This is going to be a purely technical webinar focused on extreme seeking control. So here is the information in case you want to attend that one as well. And with this, I'm going to my last slide, and I'm about 50 minutes already, a little more, where I want to summarize what it is that we are aiming to do with the colleagues and the faculty member in the Center for Wind Energy. So we definitely want to have an impact in the scholarly community of wind energy. We want to develop technology of value to the. This is an area where impact at the end of the day is going to be measured by, can we save money to this industry? The process of in great papers and producing great innovations should be done with students. So we want to use this as a mechanism to train the next generation for wind energy innovators. And already in the center, we have 16 faculty members, but this is not enough. We also have the 15 companies in WindSTAR. We have our faculty colleagues at UMass Lowell, and we continuously seek public-private partnerships to increase our capacity to perform the at this time, we have resources. We can bring new PhD students, postdocs, research scientists, other collaborators to work on capture projects. And in particular, we have two positions that we are trying to fill. One is for a postdoc or a research scientist to work on the project led by Dr. Griffith. I'm responsible in that project for the control part of the vertical axis machine. And I'm looking for someone there. If you want more information, I can send you the ad. I circulated this ad in some networks already. And we are also looking for an assistant directions for operations and business development for the Center of for Wind Energy. And there is an ad for that in the UT Dallas HR, Human Resources jobs page. And if you have any questions about this, you can contact me. Here is my email address. And with this, thank you very much for your attention.
Thank you very much for sharing your time, talent, and resources with the attendees and the community at large, Dr. Rotea. Thank you and have a nice afternoon.
Thank you very much.